Welcome back to Robert's Office Hours. Today we're going to look at an example of a nonlinear first-order initial value problem where solutions are going to exist, but they're not going to be unique. Okay? So first things first, what does the theorem tell us? Remember, the theorem says identify the right-hand side as f. Okay? So that's f of t comma y is equal to this 5/4 y to the 1/5 power. Okay, the 5/4 is a total fluke. You'll see why I put it in there in the first place when we solve this, but don't worry too much about that. It says look at f and then look at the partial derivative of f with respect to y. Okay, so what's that going to be? That's going to be 1/4 y to the -4/5, right? So what is that? That's 1/4 y to the +4/5. Okay, so I have a y in the denominator. And then it says identify the point 0, 0 in this case, so that's the origin. And it says if that's the origin in the t, y plane, can I stick an open set around this thing that doesn't contain points where f and df dy are discontinuous? And the answer is, well, no. F is continuous everywhere, because I can take a fifth root of anything, positive, negative, doesn't matter. But df dy is not continuous when y is 0, and any set which contains the origin, by definition, will have to contain points where y equals 0, i.e. the t-axis. I can't somehow find some set that comes down, somehow magically contains the origin and pops back up, but doesn't touch the t-axis, right? Because the origin is on the t-axis, by definition, any open set is going to have to contain it, okay? So my theorem for existence and uniqueness for nonlinear initial value problems fails. It doesn't apply, okay? So, well, let's see if we can solve it. After all, this is a separable ODE. It's autonomous even, okay? It's separable. So why don't we separate the variables? So let's move the y over. So what am I going to have? Y to the -1/5. And now you're going to see where the 5/4 came from. dy is integrated to 5/4 integral of dt. Okay, so what do I get here? If I add 1, I get 4/5. Dividing by 4/5 is the same as multiplying by, surprise, surprise, 5/4. So I'm going to get 5/4 y to the 4/5 is equal to, let's see, 5/4 t plus constant. Okay. Now, remember, you only have to put the plus constant on the right-hand side, because if I had a constant on the left and a constant on the right, I could just combine them into one that's on the right. Now, when t is 0, y is 0, so that would be 0, that would be 0. That tells me c is 0, okay, from the initial condition. That's what that's telling me. Okay, so now let's solve. Let's divide by 5/4. I'm going to get y to the 4/5 equals t plus, okay, if I take a constant and I divide by a constant, it does nothing. So let's call it c, and c is 0 after, we don't even need to worry about that. Okay, so c is 0, that's gone. So if I divide by 5/4, those are gone. If I take the 5/4 root, that tells me that my solution should be y of t is t to the 5/4 power, okay? So that's one solution to this whole thing. Now, if you just kind of get into this mindset of saying, oh, I'm just going to separate variables and run down this rabbit hole, you'll be like, oh, that's the only solution, okay? But if that were the only solution, then remember the theorem that we had about nonlinear existence and uniqueness would have said, well, there should be an open set containing the origin on which f and df dy are continuous. But there's not. So this may or may not be the only solution, probably not. And if you stare at it for a second, you say, okay, can you think of a function y whose derivative is equal to 5/4 times the fifth root of itself, and it evaluates at 0 to be equal 0? And the answer is, well, y of t, which is identically equal to 0, also works. Okay? That also works. It's kind of a lame solution at the end of the day. You're like, oh, hey, look, if I plug in 0, everything is 0. It's like, facts, that's true. Okay? But notice that y of t equals 0 is a solution satisfying the initial condition. So is y of t equals t to the 5/4, satisfies the ODE and the initial condition. And these two things are not equal to each other everywhere. Okay? So that's saying that what? Uniqueness fails. But existence does hold. I have two solutions here that are different. So I have solutions, that's existence, right? but I have two of them that are different, that's where uniqueness is failing. Okay? So you can kind of get this weird behavior when you have initial conditions where open sets cannot contain them for which f and df dy are both simultaneously continuous. Okay? So hopefully that gives you a bit of a flavor for how these things work and how the theorem kind of doesn't apply in this case. As always, like, subscribe, share with your friends, comment down below. Give me questions to work through, and I'm happy to post more videos. So we'll keep moving.